Hi, and welcome. We're going to talk about layer 3 forwarding concepts and routing principles. So cover quite a few things, just basically understanding a little bit about how routers forward packets. Okay, so how does a packet get forwarded from source to destination? So here we have the source at 192.168.1.10, the source IPv4 address, and a destination IPv4 address of 192.168.3.2. Okay, so initially the host is going to encapsulate this, in our example here, inside an Ethernet frame, and forward it on to its default gateway, router R1, with R1's destination MAC address on its Ethernet NIC card on the same network as our source device. Okay, so router R1 receives this Ethernet frame, goes ahead and removes the Ethernet framing information. And the first step it's going to do is examine that destination IP address. Okay. And here we're using IPv4, but the process is the same for both IPv4 and IPv6. So it's going to examine the destination IP address. And what is it going to look at? Well, the router is going to go ahead and look at its IP routing table. An IP routing table has a list of network addresses, also called prefixes. Okay, and what it's going to search for is what we call the longest match, or the longest prefix match, or longest bit match. So here, the destination IP address, the longest match in the routing table is this route with 192.168.3.0/24. So let's talk a little bit about what that means. So each routing entry includes both a prefix, the network address, and the prefix length, the subnet mask. In this case, 192.168.3.0/24 was the best match, also the longest match. Okay, it's that prefix length, that /24, that indicates the minimum number of leftmost bits that must match between the destination IP address and the entry. Okay, this is what is required for this entry to be a match with the destination IP address. In this case, 24 bits must match between the entry 192.168.3.0 and this destination IP address 192.168.3.22. So when there are several matches, the routing entry with the longest match, that entry with the longest prefix length, is what's going to be used. Okay, this is why we have, sometimes we'll see things like a default route in the routing table that actually has a /0 prefix length, which means 0 bits must match. That means basically if there are no better, longer, more specific match in the routing table, then use this default route, kind of a gateway of last resort. Okay, so next thing, the router, so once the routing table has, the router using the routing table has determined the routing entry to be used, the router needs to determine what is the exit interface, because it has to forward this packet onto either the next hop router, or perhaps if the destination address is on it, one of its directly connected networks, then onto the destination itself. But it has to figure out what is the egress exit interface associated with this routing entry. Now here we see a next hop address. So the next hop is 192.168.2.2. Let's talk a little bit about this. If a routing entry only has a next hop IP address, does not also include an exit interface, a recursive lookup may be required. Now, in today's Cisco routers, for example, Cisco, starting with iOS 12.0, uses something called Cisco Express forwarding. We're going to talk about that more in a moment, and also more in later videos. But in this case, the routing entry, even though it doesn't include the exit interface is automatically determined. Now, if in the old days, what would have to happen here, and we'll talk about this also more in a later video, but I'll kind of go over it a little bit here. What would have to happen is this exit next hop address, 192.168.2.2 would actually have to be looked up in the routing table. We call this a recursive lookup. So the router would say, oh, it's going to go to 192.168.2.2. Where is 192.168.2.2? Oh, there it is. I have that in my routing table. It actually looked that up just like it looks up a destination IP address. And then here, because it's directly connected network, and that's usually how these things would happen, that it would find that it's a directly connected network, and that's going out serial 000. Okay, but again, today's operating systems, Cisco operating systems, use Cisco Express forwarding. We'll talk more about that actually a little bit in this video. Okay, so now it needs to encapsulate the IP packet into a data link frame for that outgoing interface. Okay, so we've determined that it's going out serial 000. So whatever data link header and data link trailer needs to be encapsulate the packet will be used. Okay, this could be PPP, HDLC, whatever serial protocol that we're using here. Okay. All right, so a lot of times this is just a point-to-point serial link that I'm showing here, and the data link destination address is really nothing more than a broadcast. It says, hey, who's ever at the other end of this pipe, because it's only a point, there's only one other device at the other end of this link, and that's R2, says this is for you. Okay. But what if this was an Ethernet network connecting R1 and R2? Let's talk about that. Okay. Let's say between R1 and R2, there's actually an Ethernet network. Okay. If the exit interface is a multi-access network, such as Ethernet, the router's going to need to determine what the destination MAC address is for either the next hop IP address or the destination IP address. Okay, let's talk about this. Okay, so it's going to encapsulate it in an Ethernet frame in this topology here. Okay, so what is that destination MAC address? It's going to look it up in its ARP cache. Okay, so in this case, because it is a next hop router, okay, it's sending it to a next hop router. What it's going to be looking up in its ARP cache for the MAC address is that associated with the next hop IP address at 192.168.2.2. So that's the MAC address it's going to be looking for in its ARP cache. If it doesn't exist, of course, it will send out an ARP request. R2 will respond with an ARP reply. It will go in the ARP cache and then into the destination MAC address, and the frame will be forwarded from R1 to R2. All right. Now, let me just also mention, what if R1 is directly connected, or, you know, it would be like in R2's case, to the destination itself. The destination IP address is a directly connected network. In this case, the destination MAC address would be that associated with the destination IP address, and that's what will be searched for in the ARP cache for the MAC address. All right, so let's go ahead and just continue with our previous example. The packet will now be forwarded, whether it's serial or Ethernet, onto R2. Okay. And like I said, this may be the next hop router, or in the case of R2s, we'll be forwarding it on to the final destination of the packet. But that's the basic packet forwarding process that all routers are going to go through. Okay, so I talked about Cisco Express forwarding. Let's talk about how routers actually process these packets. Okay, so an earlier packet switching method was process switching. what would happen is a packet comes into the ingress interface and then is then sent up to the control plane, processed by the control plane. Basically, it would look it up in the IP routing table. What is the next hop address? Okay. And then it would send it down to the data plane. And also, by the way, let me mention here in the control plane would also be, in the case of Ethernet, it would also look in the ARP cache for the like the next hop IP address associated with the MAC address, just like we showed. Anyway, what I want to show here is that it will then do that same process for every packet that comes in. Okay. So it basically learns nothing each time, just repeats the same process for each packet going from the same source to the same destination. An analogy would be like getting a math problem and doing that same problem by longhand, even if it's identical every time. Not very efficient, is it? Okay, then came a method called fast switching. What fast switching did was this, okay, I'm going to send the first packet up to the control plane, the IP routing table, and if needed, the ARP cache. Okay, but I'm going to also keep that information in a fast forwarding cache. And any packets that come in with the same source and destination address, since I've already solved this problem of where to route it, and in the case of ARP, what data link address to use, I'll maintain that information in my fast forward cache. So if I see any other packets, same source, same destination IP addresses, I don't have to send it up to the control plane. I can just go ahead and process it in the data plane. Now, by the way, the control plane is handled by software. The data plane is handled by hardware. So the data plane is going to process things much faster than the control plane. Okay, so our analogy here would be you solve the problem once, math problem once, longhand, okay, time consuming, all that, but you remember the problem and the answer. So any subsequent identical problems you can just go, oh, I've got the answer, and there you go. You don't have to redo the math problem. Okay, CEF, Cisco Express forwarding. Okay, so what Cisco Express forwarding does, it takes information from the control plane, basically the IP routing table and the ARP cache and similar tables to these, and actually copies that information into something called the FIB, forwarding information base, and adjacency tables. That information is pre-populated into the data plane, which happens in hardware. So any packets come in do not have to be sent up to the control plane at all. All that information can be handled automatically in the data plane. Now, if that information is not in the FIB and adjacency table, then it will have to be, we say, punted, handed off to the control plane, which will then process it and then inform the FIB and adjacency tables of that information so it doesn't have to handle it next time. So the FIB and adjacency tables can handle it the following. Okay, so this is like CEF solving every possible problem that you can think of ahead of time, keeping it in the spreadsheet so when those problems come in, you've already solved them. You've already got the answers. Okay, I want to just mention one last thing, and that's Alex Zenon's routing table principles. Because I think as we go through routing concepts, you learn more about static routing, excuse me, and dynamic routing protocols. These are real important principles to keep in mind. First of all, principle one, every router makes its decision alone based on the information it has in its own routing table. So router R1 is not concerned about what router R2 and R3 may or may not know. It makes its decision in a bubble, all by itself. Now, that said, these are the kinds of things we're hoping to change with things like software-defined networking and things, but that's for a later discussion. Okay, principle two, The fact that one router has certain information in its routing table doesn't mean other routers have the same information. Okay, this is true whether we're talking static routes or dynamic routes. This is why it's important that you configure things properly and that the network, the routing domain, has properly converged when we're using dynamic routing protocols. Okay, so just because R1 knows how to get to 192.168.2.0 doesn't mean that R2 knows how to get there. Okay, principle 3. Routing information about a path from one network to another does not provide routing information about the reverse or return path. That's totally separate routing information. Okay, so just because R1, R2, R3 know how to get to 192.168.2.0 doesn't mean that any of that R3 or R2 know how to get back to the source, which might be 172.168.3.0 over here on the left. Okay, just because these routers know how to get here doesn't mean that R3 and R2 know how to get back for sending any return packets. Okay, so this was just some of the basic layer 3 forwarding concepts and routing principles. They'll make a lot more sense as we go through talking about static routing, dynamic routing protocols, but really important to keep in mind. Really, they'll help make sense of everything else you're about ready to learn when it comes to packet forwarding.